Hello everybody, I hope you guys are all doing well. Today we are going to be going through problem number 200 and it's titled Number of Islands. Before we go into it, these are the companies that request it most, so mostly Amazon, Microsoft, and Bloomberg, and has a very high frequency rating on the main problems page, so I'm guessing it's a pretty common problem amongst interviews. So the way we're going to tackle this is we're going to go through the STAR approach, and for those that don't necessarily understand what the STAR approach is or aren't necessarily familiar with it, STAR approach is how most interviewers would like you to essentially structure your logic when you're approaching technical questions or behavioral questions. It really helps break down your ideas into simple parts rather than just going on everywhere in a story, if it's a behavioral question, or jumping around from code to understanding the problem, so on and so forth. So you want to start out by setting up what the situation is, which is what we're going to do first. So here we're going to have a m times n 2D binary grid, which is represented by this. Binary meaning that it only has zeros or ones in this case as values within this 2D array. And here a 1 represents land and a 0 represents water. And here an island is what we want to be looking for in this case. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. Notice how they did not say diagonally in this case. And you may assume all 4 edges of the grid are all surrounded by water. That just means the outskirts of this, aka the boundaries. That's not really important in this case, but so the basic idea is that they are giving us a 2D matrix in this case, or a binary grid as they like to call it, that's filled with ones and zeros, and we are going to be tasked with finding out how many islands there are. And as they defined, an island is a sequence of ones that are connected horizontally or vertically, and so for instance, in this case, here, these are connected horizontally, these are connected vertically, this one, these are vertically connected, these are vertically connected. So this is just one island in total, and that's what the output is. And the second example here, we have one island here. It's the collection of these 4 ones. And then we have this one that's its own separate island because it's neither connected horizontally or vertically to this island here, and neither is it connected to this island here. There's a diagonal connection, but remember here we said it has to be connected horizontally or vertically. Some of the constraints: m is equal to grid.length, n is equal to grid.i.length. So it's not going to be a square matrix. A square matrix is where the rows and columns are equal. So here we may have a case where there's more columns than rows. And m is always going to be greater than or equal to 1, and then n is always going to be always going to be less than or equal to 300. And the entire grid is only going to have zeros or ones. All right. So there are a lot of different approaches to this problem. Some people may opt to do a DFS solution or a BFS solution. I found the DFS, which is short for depth first search, solution to be more intuitive, and it just made more sense to me when I was solving this problem initially. For those that aren't familiar necessarily with depth first search, if we're given a tree like this, for example, and we want to find a path, rather than going row by row, depth first search will actually start from the root node, and then it will continue down a path all the way up gets to the terminal node, or aka the dead end in this case. So if you start at 1, go to 2, go to 3, go to 4, it will continue all the way down, and then it will backtrack, go back to 3, look at the next position in its path, and so on and so forth up until it reaches the dead end. Breadth first search, on the other hand, it goes sequentially, row by row. So in the case of this, I chose to do depth first search just because it made more sense. If, for instance, we arrive at a character which is 1, which we know is guaranteed to be an island, it would make most sense to continue down this path up until we find no more 1s, horizontally or vertically. So essentially just traversing the entire path rather than going row by row. It just made a little bit more sense to me when I was approaching it. So the general idea that we're going to have is we're going to loop through this matrix here, And then once we arrive to a 1, so we're going to have an if statement that's going to say if the current position in the grid is equal to 1, the character 1 in this case, and then we want to call our depth first search algorithm, and our depth first search algorithm is going to look to the top, to the right, to the bottom, then to the left. And we'll keep calling it up until we exhaust all options, meaning that we reach a 0 if we go all 4 ways and we don't find any more 1s. And just to make sure that we don't traverse the same position more than once, every single time we finish or we go over or we search within the path itself, we find a 1, we're going to convert that into a 0 just to make sure if we're going to go up, down, to the right, and to the left in future occurrences that we find 1, we make sure to only include it within that first island, and we just don't go over it again. Because if we were to keep it 1, it'd just be a non-ending loop of it actually finding 1s, but we already went to that position, so there's not necessarily a point in going over and over it again and again. So that's the task. So our task is to find the number of islands, and then the action we just described with our solution. And now let's actually implement the solution itself. So here we want to have an integer that's going to be the, let's say, num of islands. And we're going to set that equal to 0 initially because we're not going to have any islands. Here, it's good practice to always look for edge cases. I know within the constraints down here, they already told us that m is always going to be greater than or equal to 1, and n is always going to be less than or equal to 300. And that grid is going to be non-null in this case, so it's going to be 0 or 1. But it's just good habit to check for these things anyway, just to be sure. So here we want to check if grid dot length equal to 0 or grid 0. This checks the columns. Dot length equal to 0, or we just want to check if grid is null or grid is equal to null. In this case, we simply want to return num of islands, which is just going to be 0 in this case because there aren't going to be any islands if sorry, this should be an AND. So if they're both equal to 0, mean that we just have an empty matrix. Let's see. Okay, so this checks for our edge cases just to make sure that we're, if we get some weird input, we'll just make sure to cover that early on. We could add to this if we have other edge cases that we didn't necessarily think about earlier. Here, whenever you guys see a problem with a 2D grid or a matrix, we're always probably going to have a nested for loop, so that's what I'm going to do here. This first one is going to go through the rows, the second one is going to go through the columns. So grid.length, grid.length is the rows, and r++ for int j equals 0, j less than grid I dot length j++. Here, like we mentioned earlier, in the case that we find a 1, that's when we're going to want to start our depth first search. In this case, like finding all the paths that we could possibly go from here. So in the case that grid I j is equal to 1, in this case we want to increment the number of islands that we have, and we want to increment the number of islands that we have, and we want to call the depth first search algorithm that we are going to code up right now. Into this, we want to pass a couple of things. We want to pass in the actual grid, since we're going to be searching through the paths from the grid, and then we want to pass in the index in which we found the first one. And then that's going to be all for here. And then here we want to return num of islands. So we're going to implement the depth first search method on the outside, just to make our code a little bit more modularized, make it more split up and not just have everything, the logic nested in here. So in this case, we're going to have this be private void because we're not necessarily going to be returning anything. We just want to act upon the grid here. So here we're going to call it depth first search, and then, oops, I don't need that then. Let me just take away this stuff. Cool. Okay, so this is the depth first search method that we're going to be using here. So right before we do anything, we want to check that our input is valid. So the grid, the I, and the J. So in this case, we want to check for a couple of things. One, that we are not past the boundaries of the row count that we have, and or the column row as well. So we want to make sure that the I and the J that we are going to be passing in once we go up, to the right, to the left, to the bottom is going to be valid. Because, for instance, here we're going to have a generalized logic for all of these, but for the ones that are on the boundaries, they don't necessarily have an up direction because they are at the boundary itself, or a left direction. We just want to make sure that when the call is made to go up or go to the left, that it doesn't actually go there. That'll just give us an error in that case. We just want to make sure that we're within the bounds of the matrix itself when we're making these calls and searching around it. So we want to make sure that I is greater than or equal to 0, and J is less than grid 0 dot length. Actually, we just pass an I here rather than grid 0. And here we want to check that grid I J is actually equal to 1, so we're not getting past an input that is we're getting past in a position where grid ij is equal to 0. We just want to make sure of that. And let's see. We also want to make sure it's greater than or equal to 0, but we also want to make sure it's less than the length as well. So here we do I less than 0, I less than grid dot length, and J less than grid dot length, and J greater than or equal to 0 as well. I think that is it. Let me just check my notes. Yeah, that looks like all the checks that we needed to do. Okay, cool. So in the case that I is valid, so in the case that it's within the bounds, and in the case that J is also in the bounds, so the second index, giving us the columns, and when we make sure that the value at the position ij within grid is equal to 1, here we want to make grid I J equal to 0, meaning that we already traversed this, or we already covered this in our path. So if we're here, we just want to make sure, convert this to 0. We already went here. Now I want you to look to the right, to the bottom, to the left, and up. In this case, there is no up or left, so we're just going to be to the right and then to the bottom. And then all we're going to do, it's repeated logic over and over again. And when I was looking at this problem for the first time, it didn't make sense to me at first, but after you think about it, it's a pretty neat solution actually. It's pretty intuitive. Okay, so why did I do that again? Just passing in the grid. Passing in the grid. This is the problem with copying and pasting. All right, cool. So here we want to check to the right, to the left, up, and down. Okay, So to check to the right, we want to increment the I index in this case. So if I is equal to 0, let's see. Apologies, this should be, these are flipped. So this is up, this is down, then this is right, and this is left. Sorry. So I represents the rows, right? So here we're in row 0, row 1, row 2, row 3, or row 4 in this case, but if we're starting at 0, it's going to be row 3. Here, to go to the next row, or to go up in this case, we simply do I plus 1. To go down, we do I minus 1. To go to the right, we do j plus 1. And then to go to the left, we do j minus 1. So if this is grid 0, 0, and I is equal to 0 and j is equal to 0, if we increment the row by 1, we will be in column 0 and at row 1 in this case. If we increment it again, column 0, row 2, and then increment it again, column 0, row 3 in this case. So we're checking vertically, and then we're checking horizontally as well. Okay, and in the case that this if condition is violated, we simply just want to return. Okay, now let's go through a quick run through of this before I'll show you guys the final submission, just to make sure that it passed all test cases. So here's what we're doing. Okay, these two for loops are going through the entire matrix, right? Okay. In the case that the current position, grid ij, is equal to 1, so let's say we are here initially, and it's equal to 1. In this case, we're going to increment the number of islands, right? So it's currently equal to 0. We want to increment the number of islands. After this, we want to pass in the position that we found that first one, aka our first island, and we want to pass in the current state of the grid, right? Okay. Now, once we call the algorithm that we wrote up here, okay, we want to do one thing, and that's one thing is to make sure that all the boundary conditions are being upheld and that we're not exceeding the boundaries of the matrix, okay? And we want to make sure that the value that actually we're getting is valid. Right away when we do that, we're going to be converting that position to 0. So in this case, this will get converted to 0, right? Now, all of these method calls are going to be doing the same exact thing over and over again, okay? So after we set this to 0, this is going to go, it's not going to go up or left, so you can ignore the up, this one, you can ignore this one too, because it's going to surpass those conditions, so it's simply just going to return, but it will go down and to the right, okay? So if we go to the right, for example, now this is a 1, correct? So it's going to enter this if condition again. And it's still part of the same number of islands is equal, when we incremented this, it's still part of this same call here. So this one call is due to this, and then going to the right, bottom, left, and up, it's all going to be a part of the same call just over and over again. We're going to keep calling it up until all of these are exhausted, up until all these method calls are simply just going to return because they just simply found nothing. Okay, they all converge to a 0. Like in the case here, we think about it as like we got to the dead end. There's nothing after 4, there's nothing after 5. Okay, so in this case, if we go to the right, this is going to get converted to 0. It's going to go bottom and to the right. There's still 1s. Convert these to 0s. You go bottom, you go to the right, convert this to 0, go bottom, turn this into 0, and then so on and so forth until all of these are going to be converted to 0s. This is all going to be part of the same island, right? After we're done with this this function call and it continues across the entire thing, now our for loop is going to continue. These are all going to be 0s in this case. It's not going to find any more 1s, and then our number of islands is going to be 1 in this case. Let's run the code, make sure we don't have any errors. So output 1, expected 1. Let's submit it. Yep, and there you guys go. If you guys have any questions or have any comments towards the video or my content, please make sure you guys can either send me a message or you guys can just comment in the video. I'd be more than happy to address them. And yeah, we can go through the big O of n, the time and space complexity real quick as well. So the space complexity in this case is just going to be big O m times n, and the time and space complexity are both going to be the same in this case. the solution here gives a pretty neat explanation. So m is the number of rows that we had, and n is the number of columns, and the space complexity is the same thing. The worst case situation for the space complexity, and the reason why it's m times n, is that if the entire grid map is just filled with lands, we're going to have to go through each and every single one of them in this case, aka if they're all ones, that's going to be the worst case. And the reason why it's m times n and not n squared, which is usually the case for things that involve matrices, is because this is not a square matrix like I said before. A square matrix is one where the rows and columns are equal to one another, but this is the case where they're not equal to one another, so it's m times n. And yeah, all right, thank you guys.